arcs and sectors, which of course all has to do with the circle. We know the circumference of a circle, of course, 2 pi r, and the area pi r squared. So when we talk about the complete shape, but what we're now interested in, what if we just want a piece of it? Drawing a radius here, marking our shape. Now AB is an arc. Well, in fact, I've drawn in 2 arcs there, because you've got the minor arc, the smaller one, and the major arc, the larger one. If I just look at that smaller one, so I want to find the length from A to B, and I know the angle at the centre is theta. I can just use ratio. It's the ratio of the circle. We know, if I'm talking about radian, that there's 2 pi radians in a complete circle. The proportion I want is theta. So I just multiply the circumference by theta on 2 pi. Now this of course is the advantage of using radians, because now the 2 pi cancels quite nicely and we get a nice neat little formula. The length of the arc is the radius times theta. But again, the thing we have to be careful with when using this is radians is the measure that we're using. So okay, length of an arc, r theta. Let's do the same thing with the area then. The sector, again, I've got a minor sector. The larger one would be the major sector. But the area of that sector, again, that ratio, theta on 2 pi, times our pi r squared. The pi's cancel quite nicely, and we get a half r squared theta. So there's our 2 formulas that allow us to find pieces of the circle. So a very simple example here. Now I've deliberately made the angle in degrees here, again to highlight, before I can do this, I would have to change that angle into radians. So pi on 4, 5 pi on 4 centimetres. So it's a very, very different answer to if I use degrees. So now when I'm talking about pi, I'm talking about the number pi, I'm not talking about the angle. So the length of that would be 5 times, well, 3.14159265358979323846264338327950 28841971693993755105820974992307816400628 approximately. Let's find the area of that sector. Half r squared theta, half 5 squared pi on 4, 25 pi on 8 would be the exact answer for that area. Sometimes another thing we're interested in is finding the segment. If we draw a chord in, it chops it into 2 segments. Again, there's 2 types. There's the smaller one, the minor segment, the larger one being the major segment. How would we do that? Well, it's the area of the sector, but then I'm going to take away the area of that triangle. And we've got a nice formula for that. And the reason this one's really nice is it's very similar to the actual sector formula in itself, because both of them start with a half r squared. So we could factorise that out and get half r squared theta minus sine theta. Now, some people like to remember that as a formula in itself if they're finding a segment. Others just go, oh no, I'll just remember it. It's the sector minus the triangle and just do it that way. It doesn't really matter. Up to you how you want to do it. Substitute in and we get this, well, it's an exact answer. This is where a science teacher would go crazy because they can't cope with things like that. They go, no, give me numbers. They are numbers. They're exact numbers. But there's our area, 25 pi root 2 minus 100 all over 8 root 2 centimetres squared. Here's an interesting one that appeared just last year in the HSC. So 2 circles have got the same centre, the smaller one, radius 1, but we don't know the larger one. All we know is it's 1 plus some amount, which they've called x. Let P be the perimeter. We're going to find eventually, I think, the area of that shape. First thing they want us to do is to come up with expressions for the area and the perimeter, and then show the perimeter ends up being this formula. Okay, so the area would be the larger sector, which had a radius of x plus 1, minus the smaller sector. Playing around with all that, they get theta x, x plus 2 on 2. Well, there's no mention of theta in what I'm trying to show, so I guess that's what we want to make the subject of the other one, so we can get something that substitutes in. Now let's play around with it. Perimeter equals, there we go. Alright, there we go. I've got theta as the subject. Theta is 2a x plus 2. Substitute it into my perimeter formula, and it all drops out nicely. And we get 2x plus twice the area over x. Okay, so now we want to minimize the perimeter. But in order for that to happen, that angle must be less than 2, so 2 radians. Now, you could do it, I guess, by creating a quadratic or using calculus, things like that. But I thought, oh, let's do it a different way. Let's do it just using our idea of graphs. Because I'm saying it's 2x plus 2 on ax. So imagine I was going to draw those 2 lines up. So there's y equals 2x, and 2a over x would just be some hyperbola like that. And we're saying we're going to add those together. Well, how do we add curves together? The point of intersection is always important. I'll put that up there. But I know the curve must look like that because I'm always adding to the other curve. So this actually must be the minimum point. Every other point must be above that. So there's my minimum right there. It's simply when I add those together. So now I know it's going to be when 2x is equal to 2a over x. And playing around that, I can say, well, that's x squared equals a, but x I know is a positive number. But going back to what theta was, and we get it. Because the horizontal asymptote is 2 and I'm subtracting something, I'm always going to get something less than 2. That's just a different way of approaching that question. So 11i, playing with arcs and sectors.